All right, so last class we talked about types of forces, and there are 5 main types of forces that we are going to be looking at. Normal force, gravitational force, which was, we also were given the equation, your gravitational force is equal to mass times gravitational field strength. And on Earth, that little g is 9.8. And then we talked about push force, a tension force or pull, and then frictional force. And with all of these, like push or pull or tension, I'm not going to be super picky about. As long as it makes sense, I'm happy. Drawing a force diagram, remember you have to draw a dot to represent the object. All the forces are going to be represented by an arrow and labeled, and all the arrows or vectors point away from the dot. So we talked about the bird and the skater and the other skater, and then for homework, you were supposed to do this one. So with the roller skater is now moving to the right and is speeding up. So if they are speeding up, that means that you need to have a bigger arrow going to the right because that's the way they're speeding up. So they're accelerating to the right, which means I need a bigger arrow to the right than to the left. And I'm going to call this a push on the skater by the floor. And then the arrow pulling back on this skater is going to be just a little bit of frictional force because it says there is friction. So frictional force on the skater by the floor. And then the other two forces that we have going on right now is your normal force on the skater by the floor and your gravitational force on the skater by Earth. All right, so those are the 4 forces. And then I'm going to notate that my normal and gravitational force are identical by putting 2 little lines on each of those. So that shows that the normal force is equal to my gravitational force. I will not do that for frictional force and the push force because they're not the same. So I'm just going to leave them just as is. So one thing to pay attention to is that this arrow, your push, needs to be much bigger than the friction. Okay, we'll move on to the next one. So now let's draw a force diagram for the chandelier, which is suspended from the ceiling by a chain. So the chain is not part of the chandelier. So this is our object here. And one of the things we talked about last time is that the only force that does not need to be touching our chandelier is gravitational force. So we're going to draw the chandelier as a dot. We will have gravitational force pulling it down. By the Earth. But we do not have a normal force pushing up on it because a normal force is a support force that needs to change in response. But this is not sitting on something like the floor. Instead, you have a chain pulling up on it. Well, a chain pulling up on it would be a tension force. Now, I'm specifically going to say it's the chain pulling up on it because that's what's attached to the chandelier. The ceiling is not actually pulling on my chandelier. The ceiling is pulling on the chain, which is pulling on my chandelier. So if the ceiling fell down, yes, my chain would no longer be able to pull. But as far as the chandelier is concerned, if the chandelier closed its eyes and just focused on what does it feel, it would feel the chain pulling up on it, but nothing else. Side to side, there's nothing pushing or pulling on our chandelier. So then the only two forces we have are that tension and gravitational force. I know that these forces will be equal because it is not moving, and specifically not accelerating. All right. Draw a force diagram for the bucket of water that is being raised from the well at a constant velocity. So again, with a constant velocity, we have balanced forces. That means that however much goes up is going to be equal to how much goes down. It is only during acceleration that the arrows will be different lengths. So I'm going to focus on the bucket, and I'll draw a dot from my bucket. And so I will have my tension on the bucket going up. On the bucket by rope. We'll go with rope. And then we also have a gravitational force, and these two will be the same length because it's going at a constant velocity. Again, I have no forces pushing or pulling on it side to side. So that's it. And to emphasize again, the reason why I have it by the rope is because that is what is physically touching the bucket. It's not the spool. It's not anything else that's touching the bucket. It is physically the rope that is going to be causing the acceleration. If you cut the rope, it would fall down. Then we have the basketball in the middle of a free throw. So in the middle of a free throw right here, we have our ball. And you will notice that it is, of course, always going to experience gravitational force. So I'm going to draw my ball over here. It has gravitational force. But that's it. There is nothing currently pushing or pulling on this ball in any other direction. It will be moving because it has inertia. So it was moving when she threw it. It's going to keep moving until some force exerts on it and makes it stop. But until that point, it's going to just have gravitational force, and that's it. So gravitational force on the ball by Earth. So the only way that you would be able to have another force, let's say a force pushing like this, which is wrong, would be if you actually had a hand pushing on the ball. So you would have to have her hand here still pushing on it the entire time, which would be like Halloween style, hand flying through the air to push on this ball. Hopefully now you can guess how many forces are acting on this hurdler. She's not touching the ground. She's not touching the hurdle. She is flying through the air. I have my hurdler with gravitational force, and that's it. All right, next we need to talk about net force equations.